So my name is Michel Tétu, and I am involved in business development at Reflex Photonics, a company based in Montreal, which is part of the leftover of the French culture in Canada. And so we'll be talking about, since we're a company developing optical transceiver, we'll be talking about the use of light in embedded systems. So we thought that lighting the way for embedded systems might be an appropriate title for a presentation here. So the objective of this presentation is to show how important and critical optical interconnect is becoming in the development of high-performance embedded systems. We've heard already quite a few insights about this aspect, so I'll give you more details on it. What we consider as a good application for embedded systems is the ISR systems, systems that uses a lot of sensors in number and also in of different technologies. These sensors generating a lot of data transmitted to a central computing systems. These systems process the data and dig out information out of it and decide on some action, so it sends signals to command and control units and also communication to the surrounding. As an example of a system having a huge amount of sensor, I picked up this example here, the space fence radar, developed by the US Air Force Space Surveillance Network. This is an active electronically scan array radar that detects, tracks, catalogs satellite and debris on Earth's orbits. It's not working yet, but it will be put up in a few years. So the transmitter array of this radar is composed of 36,000 independent radiating elements. The receiver array is composed of 86,000 independent receiving elements. So as you can guess, this is generating a huge amount of data. The size of these systems are such that when you look on the sketch here of the site, the roof of the small building is the transmitting array, and the roof of the long building is the receiving array. Through digital beamforming technique and frequency multiplexing and a lot of hardware and software, these systems are able to generate thousands of radar beams and also thousands of receiving beams. ISR embedded systems provides unparalleled advantage. We've heard quite a few about this already. You know about the fact that they are intelligent. They can dig information through a huge amount of data, from real-time data and historical data. They are secure, reliable, small, scalable, and they can do different tasks. The technology trend for this approach is related to the sensor, where we see high-resolution cameras and radar being put up. The processor, the capability through multi-core approach and so on, storage, sensor fusion, computing capabilities, and the size, form, and the weight and the power and so on. And I picked up another example here, which is the Argos Camera developed by BAE and partners. This camera is made out of 368 5-megabit CCD cameras that could be bought from the open market for a total of 1.8 gigapixel. These pixels and this camera is transferring information at a rate of 600 gigabit per second. To achieve that, they use 192 optical fiber at 3.1 gigabit per fiber. And just to give here an appreciation of the advantage of using optics as compared to electrical communication link cable. This picture gives a flat ribbon cable with 48 fiber terminated by an empty connector. And on its left, we see the equivalent of a 48 mini coax copper cable. So you see the difference in the volume already. But if you consider 192 optical fiber, this means that you must have 4 flat optical cable and 4 coaxial cable. So you see the difference in size and in weight already. Another aspect is the power consumption. So here we show a very rough estimate of the difference in power between optics and electric communication link. We consider here a 4-lane, 10 gig communication link, and we limit our appreciation only as what we can call the front end of the embedded computer systems and the sensor. So if we run a rough estimate of the power consumption, we end up with about 4.5 watt for the electrical link and 1.8 watt for the optical link. So this means that the power consumption for the optical link is about 1/3 to 1/2 of the one used by the electrical connection. Now, to summarize the benefit of embedded optics, on the performance side, we see that the systems are scalable up to 28 gigabit per second. They offer very low bit error rate, down to 10 to the minus 15. They are very low loss, since fiber optics is almost without loss, with 0.003 dB per meter for a multimode fiber at 850 nanometer. And the reach is up to 300 meter. They offer a small swap, because the optical transceiver is the size of a chip, so about a centimeter square on surface and half a centimeter on height. The glass fiber is very light, and then the I/O density is very impressive, because when you have already 48 fiber on an empty connector, and if everyone is delivering 10 gigabit, you see that it's a lot of throughput, I should say. And the power consumption is about 100 milliwatt at 10 gigabit for 1 unit. The ruggedness has been demonstrated. These devices can operate at 10 gigabit under industrial temperature range. They are resistant to shock and vibration, resistant to moisture, and immune against electromagnetic interference and pulses. Now, as we have already seen some introduction related to that, the VITA standard organization has considered the use of optical interconnect since already about 10 years ago, and they decided to define a standard to interconnect boards and backplane through optical link. So they defined the VITA 66.0 standard for optical interconnect. This is the base standard. From there on, those who were having some solution for the optical interconnect, they worked on specific aspects like the full-size empty variant, Airing 801, mini expanded beam, and the half-size empty variant. You see on the picture on the right of this listing, illustration of these connector, either for the board side or the backplane side. We've seen a good presentation by Mike Wamsley about this already. And there is other standards that are looking at introducing optical, possibility of optical connection. And as an example, I give here an illustration of the 67.3C, which is the connector that Mike have shown previously. Now, If we look at the picture here from Pentec, the module 5973 FMC card, they were one of the first really to use optical connection from an FMC board. On this, we see a 12-lane transmitter and a 12-lane receiver from Samtec connected to a Vita 66.4 connector. So while the systems is of a high performance, we see also that such a solution takes a fair amount of space on the boards. And there has been a pull from quite a few companies asking to try to reduce the size and the volume occupied by optical engine on a board. So through discussions, we come up with a proposal that maybe a solution that incorporate a transceiver right into the connector, right into the 66.4 connector. But this means that it cannot be designed by guys who are specialists in optics. So it needs those who have a lot of experience in designing connector. And Amphenol is partnering with Reflex in developing a solution for that, which is called the Light Connects. Now we see on the schematic on top of the board what is the solution that we are working on. We have the pale green represents the board, and the gray things is the optical transceiver. It is connected to the board through an LGA connector. And the output is an MT connector. And this is on the backplane side, which is the dark green board there, is the backplane. So the size or the aperture of the solution here for the backplane connector is convenient or meeting the requirement of the 66.4 standard. Now we, okay, so here we give a summary, if you want, of some other applications of optical, embedded optical technology in systems. So we have on the left the media converter from Amphenol, which converts the electrical signal from the backplate to optical signal and electrical signal to the front board. And here the optical connector is a 66.1 having two MT modules. On the right, upper right, it's the optical FMC board from Interface Concept that uses a 12-lane transceiver at 10 gig per lane and a 12-lane receiver at 10 gig per lane, so for a total of 100 gigabit full duplex systems. The last one is a 40 gig active optical module from Meritech that fits into the standard Vita 76, having as the input the connector size 17, and the output is an MT connector located in size 11 shell. We have example of the FMC board and that is circulating and that you can see. And I should have said in the previous slide that we have a prototype of the Light Connects developed with Amphenol that is probably circulating also. And you can have, it's a side to it, it's really a prototype, but it's moving on. Now, we've shown that optical interconnect is very interesting for many reasons. And we've worked toward more integration of optics within the Vita connector. And another aspect is that the I/O density that can be increased. So we are developing here a full duplex 300 gigabit transceiver, which means that we have 12 lane at 25 gigabit for the transmit and 12 lane at 25 gigabit for the receive. And the output connector is an MT connector with 2 rows of 12 lane for the output of this unit. So we can, I guess, say that embedded optics offers a very high performance with less swap. It's a proven, rugged, and reliable technology, and it brings some winning edge to those who dare to use it. Thanks very much, and open for questions.